Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Alright, part 21, K-nearest neighbors regression. In this part, we're going to look at KNN as a regressor instead of a classifier. So let's dig into it. In part 20, we talked about KNN model as a classifier. We discussed what are the hyperparameters, namely k and the distance metrics, and we talked about how we can optimize those hyperparameters by looking at the performance metrics in the test set. In this part, part 21, we're going to look at KNN regression model and compare it with linear regression and see in what setup KNN may outperform linear regression. And we will look at the performance metrics and basically discuss the choice of k as we discussed it for classification. In part 22, we are going to talk about cases of dimensionality. Basically, we say that if the dimension of the data set is high, it's going to be a problem, and specifically for KNN, it's going to be a more exaggerated problem. We will discuss the pros and cons of KNN, and we finally look into some applications of KNN in finance. All right, now let's see how KNN regression works. So let's visualize KNN regression line in 2D, right? And for that, we're going to work with a very simple example. There is only one feature, x, and this is our target variable y. And imagine x and y are discrete variables, right? So it can take 1, 2, 3, and etc. This is just for the sake of argument, and in order to simplify the calculations, we can do it manually. At the end of the day, the KNN regression method is very, very closely related to the KNN classifier. This means that we need to come up with the hyperparameters, pre-specify them, like say, what is k? Is it 1, 2, and etc.? What is the distance metrics, and etc., right? And the predictions are going to be the average value of the target variable in that specific neighborhood, right? So this is very simple. Actually, it's simpler than what it looks. So let's look at an example. Imagine we start with k is equal to 1. I'm going to say, use red color, k is equal to 1. And as I said, the values for x, the observations can take discrete values, 1, 2, 3, up to 13, right? Imagine we want to sort from the very right-hand side. Let's say we want to see what is the prediction of the model when x is equal to 13, right? So when x is equal to 13, then the prediction of the model is going to be equal to what? The f hat is going to be 1 divided by k, which is 1, the summation of, in that neighborhood, yi's, right? So what is, if I say that, okay, here, this is 0.13, let's say in this neighborhood, so what is the value of y? The value of y is going to be 2, right? So this is going to be 2, so the answer is going to be 2, right? So if x is equal to 13, then the prediction is going to be 2. If the number of neighbors is 1. If x is equal to 12, the prediction is going to be 2 again. If x is equal to 11, the prediction is 2. If x is equal to 10, what is the prediction? Yes, the prediction is going to be 5. Why? Because when x is equal to 10, then we look at the neighborhood. Let's say this is how we define the neighborhood, and the closest observation, well, let's do it this way. This is from 10, this is the neighborhood, and the closest observation in that neighborhood is this, and the value of y in that neighborhood is 5. So this is what's the prediction is going to look like. The prediction is going to be 5. If k is equal to 9, again 5. If k is equal to 8, okay, now if k is equal, sorry, not k, if x is equal to 8, then look at that. If I want to say, it seems that the distance from this point, let me use green, the distance from this point and this point are the same when x is equal to 8, right? So we can say, okay, the model can randomly pick one of them. Let's say the model pick this one, so the outcome is going to be, again, red. But when x is equal to 7, this is the outcome. The prediction is going to be 8, and etc., right? So it's going to remain 8 here, and then here the same story. Let's say randomly the model select this one, and then when x is equal to 2, this is a prediction. X is equal to 1, this is a prediction. So it seems that we get something like this. So this is our regression line when k is equal to 1, right? Now, let's look at another example. What if k is equal to 2? For that, I'm going to use green. So if k is equal to 2. So if x is equal to 13, so the first closest two neighbors are going to be these two. And the model is going to do something like this. K is equal to 2. So the f hat for x is equal to 13 is what? Is 1 divided by 2, and the summation of all those y's, right? So what are the y's? So I have, this is y is equal to 2, y is equal to 5. So 2 plus 5. So 7 divided by 2, 3.5. So this is what the model predict. So 3.5. If x is equal to 12, the same story. For 11, the same story. For, let's say, 10, you're still here, here. And then when x is equal to 9, actually, when x is equal to 9, then the closest neighbors are going to be, so this observation is, the distance is 2 from left. If I go 2 from right, okay, so the closest, actually, when x is equal to 9, the prediction is going to be 5 plus 8 divided by 2, right? So we get 6.5. So here, if x is equal to 9, we get, let's say, 6.5, right? All right, when x is equal to 8, then these are the same number. The closest observations are this one and this one. So the prediction is going to be the average of 8 and 5. When x is equal to 7, then the same story, because these are still the closest numbers. When x is equal to 6, here, so we have, well, actually, these two are going to be the closest. So 8 plus 8 divided by 2, we jump up here. So as you can guess, this is the same for x is equal to 5. Let's look at x is equal to 4. For x is equal to 4, then the closest observations are going to be this one and this one. So it's going to be 8 plus 6 divided by 2. So the answer is 7. So we come down here. So 7, 7. I think we're going to remain here for the rest of them, right? So when k is equal to 2, we get something like this. And then here we went up, I guess. Yeah, here we went up. And then we came down. So this is for k is equal to 2, right? So this is a regression line, right? And as you can see, it's flexible. Like classification, KNN for regression is also very flexible and nonlinear, as it is obvious here. So you can think of, expanding the idea of k. So what does the regression line look like when k is equal to 3, and etc. So in this very, very simplistic example, actually I want to show you a very cool exercise. We know that n in the sample set is 5, right? So let me call them, label them. This is point A, B, C, D, and E. So there are only 5 points, right? And if k is equal to 5, then what will happen? So basically, the prediction is going to be always one number, and that number is going to be the average value of all these y's, right? So what do we have? We have 6, this one, plus 8, plus 8, plus 5, plus 2, the entire thing divided by 5, right? So if you do the math, you should get something like 5.8. So when k is equal to 5, the model is always predicting this. So when k is equal to 5. And of course, this doesn't make any sense when k is anything greater than 5, right? So as you can see, just like the classification, when k is small, when k is equal to 1, the model is most complex. And the regression line is going to be more ragged, right? Unsmooth. When k is equal to 5, in this example, this is the least complex one because k is equal to the number of observations in a train set, and the model is going to always predict one number. This is the simplest model, right? Basically, it's equal to y bar. All right. Now that we know how KNN regression model works in practice, let's talk about how we tune the hyperparameter k, how we optimize that number to deal with the bias variance trade-off. Okay, so just like the classification, when k is equal to 1, the model is very flexible. It's very complex. And in that case, we know that the model bias is going to be small. On average, we're going to hit the target. We're going to capture the pattern in the data, but the variance is going to be large. We say that the model variance is large. It means that if you repeat this exercise with just another subsample of the data, the model is going to change. You know, the f hat is going to be different, right? The predictions are going to be very volatile, right? So this is when k is equal to 1, and not surprisingly, you know, we know how these things are calculated now, right? So it's the regression line is going to go through all the observation, and for that reason it's going to be very flexible. Okay, we know that the model variance is super high now. Now as k grows, we deal with a less complex model, and the regression fit is going to become smoother and smoother. This corresponds to low variance and high bias. Okay, so let's say k is equal to 10, and as you can see, this regression line is smoother now. But it's still, compared to linear regression, is going to be very, very, very jagged, right? It's go up and down. Okay, then let's say k is equal to 50. So this is a lot smoother than compared to k is equal to 10, right? Now here, we talked about an exercise in the classification. Let's repeat that exercise for regression as well. Let's say k is equal to, let me use green. What if k is equal to the train size? So let's say the data in the train size is, I don't know, in this example, let's say we're talking about 300 of these blue circles, right? If that's the case, what is the prediction? What is y hat? How does the regression line look like? Okay, so I'll leave it as an exercise for you. Then let's see how we can optimal the value of k. So we're going to report the RMSE versus k. Right? So now in this example, because I'm using k and not 1 over k, as we go from right to left, the model is going to become more complex, right? More complex. Because we're reporting k. In classification, we looked at an example that we were looking at error rates compared to 1 over k. But here we're looking at RMSE versus k, right? Then I'm going to plot two things here. RMSE cross-validated version and RMSE in the test set. We are not interested to report the RMSE in the train set, right? Because we know that the RMSE in the train set is going to get closer and closer to 0. Okay, look at this one. Let me use red color. So if I report the RMSE in the train set, well, the model is capturing all the nuances up and down because it's super complex. The RMSE is going to be very small. So we know that if I want to plot the RMSE in the train set, it's going to be something like this. Always converges to 0. So there's no point of doing that, right? We're going to report RMSE in the cross-validated version and the test set and plot it versus k, right? And this is how it's going to look like. And as you know by now, we most of the time look at the RMSE cross-validated version when we want to tune the hyperparameters, right? So let's say that's the case, and this RMSE is minimized at this point, and at this point, let's say k is equal to 3. Okay, so we get the optimal number here, and this is our RMSE cross-validated version. Okay. If you're curious to know why I prefer to use the RMSE cross-validated version versus RMSE test set, I encourage you to watch our part 6 where I talked about cross-validation in machine learning in general. But the short answer is that, you know, the cross-validation is used for tuning hyperparameters because we need to use the validation set to optimize the parameters, and at the same time we want to report the performance metrics in the test set on the data that the model has not seen before. So the answer is going to be cross-validated data. And another important reason that I prefer to use cross-validation versus test set is that what if the test set is small, right? Then we know that if I do 5-fold cross-validation, we can report the RMSE and the standard error of RMSE using cross-validation. So I know that, for example, RMSE, let's say in this example, we're going to say k is equal to 3, then RMSE in the test set, let's look at the brown line. So let's say this is the RMSE. RMSE in the test set, let's say it's I don't know, maybe 55. And RMSE cross-validation is going to be equal to 62, right? We know that RMSE in the test set, maybe in this example, is smaller, but this is one number that I can get by looking at the RMSE in the test set. However, if I calculate the RMSE in the cross-validation, depending on what is the k-fold, let's say we're looking at 10-fold cross-validation. So I have 10 of these numbers. I can report the standard error of the RMSE. This is going to be a lot more informative. So I have two statistics now, right? The standard error and the average. Let's say the average is 62 and the standard error is some number, I don't know, 3. Then this is a lot more informative comparing to when I have only one statistic in general. So I prefer to report the not only for KNN model, for any other machine learning model, when I want to tune the hyperparameters, I prefer to use cross-validation and report the cross-validated performance metrics. Let's say the RMSE in the test set for classification accuracy, the cross-validated RMSE, cross-validated accuracy, and etc. All right, look at KNN regression in 3 dimensions. Now we have x1, x2, and our target variable. Okay, so the same story. When k is equal to 1, the model is very flexible, low bias, high variance. As k increase, the model becomes less flexible, and the regression fit gets smoother and smoother. And this corresponds to a low variance and high bias. So I want you to think about, pause this video and answer these questions. So one of them, in this example, one of them, k is equal to 1. For the other one, k is equal to 10. So I want you to tell me in graph A, what is k? And in graph B, what is k? Okay. All right. So I hope you got the right answer. So here k is equal to 1. If you see, the regression surface is going to be very flexible, goes up and down. And this is k is equal to 10. So the regression surface is going to be less flexible and it's going to be smoother. Okay. All right. Now let's conclude this episode by comparing linear regression versus KNN regression. Imagine the black curve is the true relationship between y and x. So we know that the true relationship is linear. Okay. In general, the true relationship is not observable. This is what we are trying to estimate. But let's say, for the sake of argument, this is a true relationship. Okay. And the green dashed line is going to be the MSE in the test set when we use KNN, right? So let's say we are going to report the MSE in the test set, and not surprisingly, we're interested in the performance of the model in the test set, right? Not necessarily in the train set. And let's plot the MSE in the test set versus different values of k, and we're going to report these numbers as 1 over k. So this is going to be the most complex model when k is equal to 1. And here, so for example, k is equal to 1 divided by 5, right? So k is equal to 5. Is equal this is 0.2 and etc., right? So this is the most complex model, most complex. And the green dashed line is our MSE for the test set for different values of k, right? So if k is equal to 1, we are here. We know that the performance of the model in the test set is the worst, right? The MSE is the maximum here. Why? Because the model is unnecessarily complex. And let me actually try to show you that regression line here. Let's say this is if k is equal to 1, right? The regression line is going to be something as funny as this one, right? So it's going to be basically it's capturing noises, right? So when k is equal to 1, we know that the performance of the model in the test set is going to be the worst in the test set, right? Because yes, the model may be the bias is going to be small because on average we're hitting at a target, we capture the pattern, but the problem is that the model bias is going to be very large, as you can see. And when that's the case, the MSE, which is a combination of model variance and model bias, is going to be very large. So we are here. Then as we increase k, we go to the left, right? So as we increase k, we go to this direction. And it seems that the MSE in the test set is going to decrease. Okay, so this is how the MSE in the test set is going to look like for different values of k. Now, what is the black dashed line? The black dashed line is the MSE in the test set when we use OLS. So if I use OLS, This is, let's say the MSE in the test set is 0.9. MSE in the test set for when we use OLS is 0.9. And of course, not surprisingly, it's independent of the value of K, right? Because we are using OLS, has nothing to do with K. So we're gonna get one number, and that one number in this example is, well, not 0.1, 0.09, it's 0.09, right? So it seems that when the true relationship in the data is linear, KNN, regardless of the value of K, is not performing as good as our simple OLS, right? So KNN is going to always do a worse job compared to a simple OLS when the true relationship is linear. Now, what if the true relationship has become more and more nonlinear? So what does that mean? So the more nonlinear true relationship, the better performance of KNN compared to OLS. Let's look at another example. So imagine here the true relationship is this curve. This kind of S curve is a true relationship. And now for some values of K, specifically for these values, KNN is outperforming the OLS, right? Because look at that. So it seems that, let me use my laser. So it seems that for these values of K, the MSE in the test set for KNN is smaller than the MSE in the test set when we are using OLS, right? So in this region, when K is equal to between these two numbers, so KNN is outperforming the OLS. Why? Because the true relationship was more nonlinear. So if you make the true relationship even more nonlinear, so let's say we have something like this, right? And then it seems that for any values of K, the KNN is outperforming the simple OLS by a large margin, right? For different values of K. So at this point, you might get excited and say that, wait a minute, why don't we use KNN as a regressor all the time compared to OLS? Because look at that, when the data is nonlinear, KNN is doing a very good job compared to OLS. So what do you think about that? You might want to say that, okay, so KNN is a non-parametric model, right? Non-parametric means that we are not imposing any kind of functional form to the data. So it can be as flexible as possible. And yes, that's the case if the true relationship in the data is nonlinear, then non-parametric models are going to do a better job compared to parametric models like OLS, right? Because imagine this is our OLS regression line. Okay. However, be very careful, guys. Here, the dimension of the data is only 1. And yes, if the dimension of the data is 1, and if the true relationship, for whatever reason, you know that the true relationship is nonlinear, then you might want to use KNN as a regressor. But in real world, in most applications, we are dealing with the data in very high dimensions. Let's say dimension is 100, 200,000. And then when that's the case, the KNN is going to do a very poor job because of the curse of dimensionality. So we're going to talk about the curse of dimensionality, which hit the performance of the KNN models in general in the next episode. All right, so in part 20, we talked about KNN classification. In this video, we covered KNN regression, and in the next one, we're going to talk about the pros and cons of KNN. Until then, take care. See you in the next one.